Okay, so if you're still with me, we just messed around in GeoGebra. We plotted some lines that are orthogonal. All of them were orthogonal to the same given line. And we can sort of see that there's a plane taking shape. And what we want to do now is find the equation of that plane. So let's think about how we can do that. So what I want you to do, whatever you're writing with, take it, put it perpendicular to the desk or the table or whatever you're writing on, right? And so imagine that you have a lot of points on that thing, the thing you're writing on. So what I'm going to do is I'm going to put a lot of points. So I'm going to draw a piece of paper, right? And on the piece of paper, I have like a lot of points. And now imagine my stylus coming like straight out of the screen at you, right? So it's perpendicular to your screen. So what I can do is I can take any of these points, any pair of these points, and make a vector, right? A bunch of vectors. They can be different colors. They can be the same color. It doesn't make a difference. All these vectors. Every one of these vectors, they have like no relationship to each other, right? Two of them actually kind of look parallel, but you know, there's nothing really definitive going on here. But every one of these vectors, with the vector coming straight out of your screen, if we do the dot product, we are guaranteed to get 0 because this vector is orthogonal to the screen. Or for you, where you have your pen or pencil, vertical, just vertical, perpendicular to the desk. Every vector that you can draw on your desk, if you dot product it with your pen, will give you 0. So we can actually take that idea of like any vector that we make out of 2 points, and we can write the equation of a plane. So let's see if we can do this. So we know, in our case, this direction vector, let me switch colors. This direction vector is sort of like your pen to your desk or table or whatever you're writing on, right? So that's like your pen perpendicular to desk. So what I want to do now is I need to use 2 points that are in the plane, and I'm going to make a vector out of them. So the 2 points that I'm going to choose to use are going to be, so I'm going to borrow this. So let's say that this point is the point X, Y, Z. It's just some random point in the plane. And then let's say that this point is 1, 6, -5. Okay, so I have 2 points. So what I can do is I can make a vector between them. So I'm going to say that it's the vector from 1, 6, -5 to XYZ. So I'm going to do XYZ minus 1, 6, -5. So it's like this vector, fill it in. So that vector, that doesn't look much like a vector, but that's the vector that we're going to make. So that vector is going to be a vector in the plane. So vector in the plane. So a vector in the plane is something that I say all the time. It's a vector that's parallel to the plane is really the correct thing to say, because once you have a vector, as long as you don't change its magnitude or direction, you can pick it up and move it down and left and right, as long as you don't change its magnitude or direction. So it's not strictly speaking correct to say vector in the plane. I say it all the time, and I think it helps people learn, and I don't think it hurts anybody. So our vector is going to be x minus 1, y minus 6, z plus 5. And then we are saying that every vector that's in the plane, if we dot product them, remember the stylus coming straight out of the screen, dot product it with any vector on the screen, we're going to get 0. So a generic vector in the plane dotted with a vector orthogonal to the plane should give you 0. So if I dot this with the vector -3, 4, 7, I should get 0. That's it. That's an equation of a plane. It looks insane, but the equation of a plane is like, and the equation of a line in 3 dimensions, they're super geometric. Like if you can remember where they come from, right? Like a line is it's all, you have a vector parallel to the line and a point on the line. It's like all vectors you can create from the line are going to be parallel to that vector. Definition of parallel vectors is they're scalar multiples. So it's like generic vector equals t times parallel vector, done. In this case, you got all the vectors that are in the plane. If you dot them with this vector, you're going to get 0. So that's what we do. We make a generic vector in the plane, dot it with this vector, and we get 0. So you don't leave this usually. So what you usually do is expand it. So I'm going to do that. So -3. So I'm doing the dot product. It just looks weird. Y minus 6, 7, z plus 5. Ew, that doesn't look like. Plus 5 equals 0. Typically what you do is expand this. So I'm going to do that. You could stop there though. This is called point normal form. And it's a lot like point slope form of a line, right? Like you can look at it and see the vector -3, 4, 7 in the coefficients. You can see the point 1, 6, -5. So it's a lot like point slope form, which is in my brain how I think about it. So I'm going to do -3x plus 3 plus 4y minus 24. So what I'm going to do is I'm going to get standard equation of a line. And hopefully I don't mess this up. But if I were a betting man, I would say that I might make a mistake here. Because who does a lot of arithmetic? So -24 and 35 is 11. And then plus 3 is 14. And then I'm going to move it to the other side. So -14. In life, you usually want to multiply through by a negative here. But I think we're okay. What I'm going to do, I'm going to go back to that GeoGebra sketch that we have going. So back over. I hope you saved it. I am back over here, and I'm going to try adding that. So I'm going to graph -3x plus 4y. This is like the moment of truth. -14. How does it look? Ah, look at that. All of those lines are in that plane. That plane contains every possible line that is orthogonal to our given line that passes through the point, whatever the point is, 1, 6, -5. It's every line. So like one way of thinking, the way that I think about it is like, you know, in like movies sometimes when somebody has like a staff or whatever and they start like spinning it really fast, like the way it spins kind of like creates a plane. That's sort of what we did. So that's pretty good. I'm gonna go back to the notes, and I think that we could finish the next problem in this video. So let's try to do that. Let's find out. Let's see what we're made of. All right, here we go. Back to the iPad, back to the notes. All right, so now I'm giving you 3 points. Fun fact that you already know, but you probably have not thought about maybe ever. Any 3 non-collinear points determine a plane, which is kind of like saying a triangle determines a plane. And I've always been very comfortable thinking that because it makes a lot of sense to me. Like that's why like you can use a tripod to hold things up. So let's use these 3 points. We're going to make 2 vectors, right? So both of these vectors will be in the plane. So I'm going to say this is like A, B, and C. I'll make the vector AB. So AB, so it's B minus A. So it's going to be 6. And then 4 minus, so 2. And then -2 minus, so -7. And then it'll be AC. It doesn't matter, but I always use the same initial point for both of these vectors. I think it's like for clarity of mind, like it's easier to remember and check and all of that. Plus your picture, then you just have 2 vectors coming out of the same spot, so it like feels better if you're picturing it, I suppose. All right, so 6 minus -1, 7. 1 minus 2, -1. 3 minus 5, -2. Okay, so I got 2 vectors. I could have made the vector BC. I could make the reverse vectors, whatever. I just need 2 vectors. So I have 2 vectors. Now what I want to do, so both of these vectors are in the plane, right? Like I have no way of showing that. They're both in the plane. Like you could draw both of them on paper. So on the same sheet of paper. Now what I want to do is try to find a vector that's orthogonal to the two vectors that I found. And I want it to have the components a, b, 1. So this is like a degrees of freedom type of thing. When I needed to find one vector that was orthogonal to another vector, if you think of what we did, we made up two of the values. So we said like, it's 1, 1, c. And then we would dot product the vectors and solve for c. And that worked because we only need one vector. Or we were only using one vector, I should say. Now we're using two vectors. So I need it to be the case that I need two things to be true, right? I need 6, 2, negative 7 dot ab1 equals 0. I need that to be true, but I also need 7, negative 1, negative 2 dot ab1 equals 0. So if I had done like, for the top equation, if I had done a comma 2 comma 1, I could solve that equation. I could do the dot product, set it equal to 0. I could solve for a. But the value of a that I get is not guaranteed to make the second equation true. And the same thing would be true for the second equation. If I like just decide to do like 15, negative 13c, and then solve for c, the value of c that I get won't necessarily make the vector that I'm finding orthogonal to the other given vector. So I need two unknowns so that I can solve a system and get the values that work for both of them. So that's like a big idea. So let's actually solve this. Let's see how bad it is. I might solve it on a calculator. So I get 6a plus 2b minus 7 equals 0. And I get 7a minus b minus 2 equals 0. Do I want to solve that by hand? I mean, I don't want to, but I think I'm going to. So I can just double this and then add down. So that'll be 14, that'll be 20a. And then the b's cancel out. That was like the whole idea. And then minus 11, I think, equals 0. So I'm going to get, oh, this is terrible. I get a is 11 over 20. Okay. And then if a is 11 over 20, I don't want to do this. I'm going to use a calculator. Ready? Well, maybe I should power through. Would that be teaching you a lesson? I don't know. I'm teaching you a lesson either way, right? Like sometimes I'm gonna use a calculator in the interest of time, right? I don't want to take your entire life solving this. It's not that I'm afraid of solving that system. Here we go. So back to the calculator. I'm going to solve. So I'm going to do menu 3, 7, because that's the easiest way to solve a system of equations. And then a and b are my variables. And then 6a, you could just use x and y. Like it wouldn't make a difference. 0. And then, you know what I should have used? I should have used Cramer's rule. Cramer's rule is super fast. It's like a superpower. Cramer's rule? Yeah, Cramer's rule. Get this. 11, look at that. I got 11 over 20. So like nothing to be afraid of. And then I'm getting that b is 37 over 20. And so my vector that's orthogonal is 11 over 20, 37 over 20, and 1. So obviously, if you're going to do anything with this, you would multiply through by 20. So the vector we would use would be 11, 37, and 20. Okay, so this is a vector that's orthogonal to the plane, right? So if you drew everything on your desktop, it's orthogonal to your pencil if your pencil is orthogonal to that, so like perpendicular. If you drew it on your computer or your phone or wherever you're watching this, if you draw all of the vectors there, this vector is coming straight out of it, the dot product will be 0. So now I want to write the equation. So all I need is a generic vector in the plane. I can use any of the 3 given points. Oh, actually, I'm not even showing you the iPad screen, so you don't see any of this. But I'm definitely not redoing this. So here we go. Share, and there's nothing exciting going on. I just wrote it down in poor handwriting anyway. You're better off if you were just listening and writing on your own. Okay, so I got this. All right, so I can use any of the 3 given points. So I could use I'm gonna use 613 because they're all positive, but like doesn't make a difference. So 613, generic vector, which I'm gonna write that. Generic vector, this is a generic vector in the plane, is gonna be x minus, what did I say, 613? X minus 6, y minus 1, z minus 3. Let's check that, 613, okay. And then I need to dot product the generic vector with the vector normal or orthogonal to the plane, and that dot product should give me 0. So x minus 6, y minus 1, z minus 3, dot product 11, 37, 20, better give me 0. That's one form, not the preferred form. I'm going to expand that a little bit. 11, x minus 6, plus 37, y minus 1, plus 20, z minus 3 equals 0. All right, that's my equation of the plane. To check it, do I dare check it? I'm going to switch over to GeoGebra for a second. I'm going to start a new thing. So let's do file. Let's go new. Don't save. Never save. You should always save things. And what am I going to do? I'm going to plot the point. So 11, x minus 6. This is like a, I don't know what it means for it to be a big plane, but like these numbers are big. Y minus 1 plus, you can see it starts guessing what it thinks you mean. It's like almost never right, but I applaud it for trying. There's our plane. Okay. And now what I'll do, I guess, I'm going to plot those 3 points. So let me see if I can get those. So I think that the point -1, 2, 5 is in the plane. I think that the point 5, 4, -2. This is so nerve-wracking because it's like, this is when I find out if I have to remake this entire video. 2 for 2, and then 6, 1, 3. There you go. That is the plane that contains those 3 points. So that was a good one. I'm going to stop there. I will come back. I'll do more of the notes with you. I hope you're finding this helpful.